Alrighty, I will begin with a word of prayer. I think we are getting a late start because of nonsense. Sorry about that. Alright, I'll begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. I just pray that you just help us to draw together our thoughts about compactness and just wrap up our study of that. We thank you, Lord, for your many blessings to us. In your name I pray, Lord Jesus. Amen. Okay, so we had covered the rudiments of compactness last time. And now we've reached all the way to section 4.5, which is on the theorem of Wallace. So this is a very, very neat. And so last time I advertised we were going to do something with the diagonal. It never happened. That's because it was the proof of Wallace theorem. That's where the diagonal come back out again. Anyway, here it is. So you got a topological space, actually two of them. Theorem 4.47, again we're in, as usual, what is this? Marco Manetti. Man, I love that name. Wallace. So Wallace's theorem. And here's what he has. It's got a topological x and y topological spaces. All right. And we have subsets. A subset of x, B subset of y, and what else? Oh, compact. Compact subspaces. What's that mean? Just remind me. What does it mean for those to be compact subspaces?
Every open cover. It's a finite subcover.
Right, every open cover admits a finite subcover. Exactly. Oh man, I was just thinking about something about connectedness. What's wrong with me? Oh. I have good company. I'm like the smartest guy I ever knew once. And I mean, no offense, you guys, but I'm sorry, but this Daniel is. I don't know where he is, but man, that guy, he knew so much. But this one day, he could not remember the definition of compactness for like 2 hours, and he was just the funniest thing to watch. He was so mad at himself for not knowing the definition of compactness. It was so fun. All right, I digress. So you got this A and B, and then you've got also W open in the product topology such that a Cartesian product with B is a subset of W. Okay. All right. Then, Then there exist open sets U and V in X and Y respective, such that U contains A, V contains B, and U cross V is a subset of W. So this is all the if. And there exists U subset of X, V subset of Y, such that A is a subset of U, B is a subset of V, and how's it go?
U cross V is a
Subset of W. Yeah. I guess I could hazard a picture of this. It probably would be a mistake, but I'm going to try. So, A and B compact might be something like, this might be a picture of A, right? Maybe this is a picture of B. Right? Or I suppose a picture of B could be something like, oh, I better not. Yeah, I'll do it. So there's a compact B as well. All right, and you take the Cartesian product of these. Now, this of course is inside where? So this is inside R, right? This is inside R2. And so you could look at something like the Cartesian product of this would be something like Yeah, exactly. Like it's a finite cylinder actually would be something like that. You could think of it that way. So here would be A cross B. So there exists.
There's also a W that contains A cross B.
Yeah. Do I have this right? A is a subset of U.
Yeah.
So, yeah, there's a W, right? Like it's out there, man. W. No, I mean, I guess the W is given an open set, right? We don't have much fine print on that except that it has to contain the Cartesian product of A and B. Then there exists U, which contains X, so the U is something like, in my picture, something like this, right? And V could be something like this, right? I mean open, right? Sorry, open. Fix it. Sorry, I should stop wasting time with all this picture drawing, but it makes me happy. And then what? U cross V is, so U cross V would fit in here something like, here it would be like a loaf of bread. It seems like a reasonable theorem when you think it through like this and look at an example. It seems totally reasonable that that should be able to be done. Yeah. Proof. Nathan's like, them's fighting words. No, I'm sorry. That would be more your compatriot there. Mike will be like, what? Proof by picture? Never. Something like that. I don't know. Actually, I've never really seen Michael get that irate about something mathematical. Does he? No, he seems like the kind that could go on a proper rant.
Yeah, he goes
Yeah.
on rants.
Okay.
But like,
Mm-hmm.
like it's not anger per se. Like he just gets frustrated, I
Ah.
guess. That's
He's
his
a man of principle.
Yeah.
Anybody who's a Rand Paul supporter's got to be a man of principle. It's here. Baga? What? Okay. Baga to you too. That must be probably
Baga.
something horrible in some language. All right. Proof. Consider first a special case where A is point. All right. So, why do we have to think about that? I mean, I guess a point is compact. Could be compact, I suppose. So I don't know. Interesting. So he starts by thinking about a special case. A is point. What? They're just talking about posting video on YouTube for some random reason. Somewhat ironical. Let's see here. Hey, that's a valid.
YouTubeception.
Ironical is a valid saying. Is not. I can't take credit for that. That is very much. That is a Dr. Wing saying.
Oh, okay, yeah, okay,
And
that's
it is
what
one
I
of my
meant.
favorite sayings of Dr. Wing. It's usually said something like, "It's very ironical." I love it when he says that. It makes me happy. So here, where are we? I don't know. Why is he looking at a point? For any B and B, there exist two open sets. So what are we assuming? X and Y topological spaces. A is this. All right. I'll keep going. He says for any B. In B, there exist two open sets. He calls them UB, subset of X, and VB, a subset of Y, such that the pair A comma B is an element of UB across VB, subset
It's 4:00 p.m.
W. Where's the... I guess W is a... What is W is a... What is it? It's an open set which contains A cross B. So if W is an open set which contains A cross B, I mean, certainly it has pairs that have A in it with something else over here. I'm not sure where... Where's this U? Can you guys tell me where these open sets UB and VB coming from? No, I'll keep going here. I guess this is the thought's not complete yet. And he says the open family. Why do there exist these open sets? I'm sorry. Okay, keep going. The open family. I should persevere a little bit longer. Open family VB such that B is in B covers B. Where are these V's coming from? I'm sorry. I guess he's just saying take a family of open sets, right? Take a family of open sets in inside Y, right? Each one of which contains B, right? Then these why would they cover B?
Because there's one for each element of B.
Oh! Oh, goodness gracious. Thank you, Daniel. I was thinking of B. I was thinking of B as being fixed here. Oh, wrong. B is a variable, and it's, of course, as it traces out, I mean, you're going to cover all of, oh, yes, of course. Idiot. What's wrong with me? Many things. I see here. Now, if that's an open family which covers B, this covers B, right? It's an open cover of B, right? There exists finite subcover, right? Say VB1, VBN, which covers B, right? Fine. Still a little bit lost on why could we find, where did the UB come from?
I feel like UB could be the same every time.
Yeah. I mean, it has to contain A, right? Okay.
Yeah, I think it might just be a property of like product topology.
Right.
It's just that there, for each point, there is.
You know what? I'm stupid. It goes back to what's a topology, right? The fact that A is a point in the topological space X, right, means that there exists an open set which contains A. So you can take it to be that set, right? I mean, there's a notion of covering built into the definition of topology, right? Part of the definition of topology basically posits the existence of an open covering for the whole space. It's not possible to have like a point in the topological space which is not contained in some open set in the topology. That is forbidden. So the thing I'm worrying about is absurd. Okay, so
I mean, except that it's also contained in the W, so yeah.
right.
So I think that does come from like properties.
Oh,
of product
yeah,
topology.
and so W, right, W is open.
That means AB is an interior point, right? So there is an open cell like that.
Yeah. Okay. So then what? we've got this finite subcover of B, right? Such that B is a subset of the union of these, right? Because these aren't necessarily inside. These aren't necessarily just within B, right? So it could go a little bit beyond B. So certainly B is a subset of the union of these. And then what? And he says define the open sets UB1 through UBN. Likewise, like you were saying, because W is an open set in the product topology, that implies the existence of the UB1, UB2, UBN. All right. So W open implies that there exists UB1, UBN, and then what did he do? He says define U as the intersection of the UB1 through UBN, and V as the intersection of the VB1 through VBN. All right. And then
the union.
what's that?
It's the union.
Oh, you're right. Yeah. Sorry. I would have gotten very confused very soon. And then what? And then he makes a claim. He says that the singleton A cross B is a subset of U cross V. Man, all of this for just the special case that A is a singleton. Right? All right. Do I believe that? Let's see here. A is in every single last one of these, so it's in the intersection by construction.
And B is covered by all of those, so it's...
Right, yeah, B is a subset of the intersection, so we have what's needed for both components of the Cartesian product, so by component-wise thinking, which is, after all, the Cartesian product is defined, right, is sort of component-wise thinking. And then what we got? Subset of the union. So then he replaces U with its union. So this is a subset of the union, I equals 1 to n, of UBI, Cartesian product with VBI, which he says is a subset of W. Now that's by construction, because each one of these guys is a subset of W, so if you take the union of them, they're again a subset of W. So what's that get us?
Oh, we have the U and V.
Oh, okay, so then we've done our job. We got the conclusion. We found an open U and V inside X, inside V, that contain A and B as advertised, and their Cartesian products inside are a given open set. Okay. Now what's his next? So he's like, okay, somehow in the next 4 lines we're going to prove it for, now that we had all of this for a singleton, like 3 lines get an arbitrary compact set. How is this? I'm curious to see how this works out. He says, in the case A is an arbitrary compact set, we've shown for any A in A there are open sets U sub A, V sub A, such that, all right, so let me, I need to erase a little bit. Well, I guess I can write up in the corner. So he's like, so for A compact, we have for each A in A, right? There exists UA, VA, open, right, in X and Y respective, right? with what?
So we found the last one.
Right. So we've got what? Yeah, like we said. So it's A cross B is a subset of this UA cross VA, right? And the subset of W for that given W, which does what? I mean, W here has to be assumed to be containing the A and the B, right? Yeah. Oh. So then he's like, but then what you can do, there's a lot of crazy people out there today. What we got then is that the family, so he's like, but if you look at this guy, that gives open cover of A. Because for each A you have an open set which contains that point, right? And if you just do this over the whole A, of course you got an open set around each point, you got an open cover. But A is compact, right? So that means that there exists a finite subcover, right? We can find, say, UA1 union UA2, union UAM equal to A, right? Well, I guess it doesn't have to be equal to A, but it could be A is a subset of it generally, because the U's are not supposed to be subsets of A. They're open in the ambient topological space X, and I mean, if you want an open cover of just open sets in A, you could take these U's and intersect them each with A, and then that would give you an open cover of things just in A. That's not a big deal. That's what I'm talking about. So then what? Then the same thing as we did down here. You take the corresponding V, VA1 through VAM. This is this is the U. And then the V you just get from VA1 intersect VA2 intersect of that intersect VAM. And that's the U and the V for Wallace's theorem, where the V's are connected to the U's just like they were in the previous argument. Oh, my advertisement of the diagonal argument being present in Wallace's theorem, I guess you have to look really, really hard to see it. Like, it's not there. So, that was wrong. Sorry about that. Oh man, I got the diagonal argument on my brain. We're going to find it eventually in here. Can I erase?
Yeah, what are you going to tell us the philosophy?
Oh, yes. My brother was impressing on me that I should impart to you this wisdom, which is that when you think of compactness, a good heuristic is to think that if something's compact, it's finite. Now, of course, every finite set is compact. We talked about that last time. But on the other hand, when you have things that have compactness, there's a certain finiteness to it, right? And we even saw that in like arguments we made. That finite subcover allowed us to, on the real line, find a min and a max. It's finite. It can't go on and on. That's actually a very useful comment.
Made it seem that way like as soon as we started talking about it the other day.
What's that?
It made it seem that way when we started talking about it the other day. Definitely.
Yeah.
Started to head that direction very early.
So I didn't say that precisely, but I mean, it's kind of like, it's in the water, I mean, like.
Is today shortened period?
No? I don't think so.
Oh, okay. Oh, you only changed it for that week.
Oh yeah, just that one, I'm sorry.
Oh, okay.
That was because I had,
Capstone.
yeah, I had to go to the capstone thing. I am the sole professor
So I thought it was like a
for that course next semester. You take that course yet, Daniel?
no. I'll take it next spring.
Yeah, I may not be. Who knows? Maybe I won't be doing it by then. You'll be safe. I'm just kidding. It's only an hour credit. What can I do with an hour?
A lot more than most.
I'm sure you'll find something.
I'm just hoping to get a little more organization to it. And hopefully actually meet every week. Because we keep missing weeks. Because we forget to communicate who's doing what. No! And all of a sudden we're not meeting. Alright, let me move along here. Sorry. Any compact subspace of a Hausdorff space is closed. What? Corollary. 4.48. Any compact subspace in a Hausdorff space is closed. Compact subspace of Hausdorff space is closed. All right, so I need to remind us now a couple little things. First of all, let me remind you that we had this theorem 3.69. In theorem 3.69, what we learned was that a topological space is Hausdorff. Oh, I don't know if this is the one I want, actually. I'm just reminding you. This may or may not be relevant. I'm pretty good at making irrelevant comments today here. A Hausdorff space is topological space is Hausdorff if and only if the diagonal is closed in the product. Let me remind you what the diagonal is. The diagonal, this delta, it's the set of x comma x such that x is an x. So that's the diagonal. So apparently x is Hausdorff if and only if the diagonal is closed in the product topology. All right, so that's useful to us because then when we're studying compact space, we were trying to prove this corollary 4.48, right? Compact subspace of Hausdorff space is closed. Well, we can use this theorem as a tool to understand how to do that, right? Let's see here. And all of a sudden my shoulder hurts. What's wrong with me? All right. Let's let A subset of X be compact in Hausdorff. What did it mean for X to be Hausdorff? Do you guys remember?
Any points contain two open sets that are disjoint, essentially?
Yes, for any distinct pair of points, there exist open sets which contain those points and are disjoint. Yeah. So yeah, it's Hausdorff. You can separate points with open sets, disjoint open sets. So we have a compact subspace of a Hausdorff space. Now we're supposed to show what? We're going to show A is closed, right? See, I'm going to need something. Fine. I thought it was more direct. Take my medicine. Fine. Alright. He says, to show A is closed, we'll prove that if X is not an element of K. Right, so suppose I said K, I mean A. Suppose X is not an element of A. He has K instead of A in the book, all right? He says we'll prove that if X is not an element of K, there's an open set U in X such that we haven't proved it yet. We can prove, all right, that there exists open U in X such that X is an element of U and U intersect A is empty.
Should show that any element of x minus a being an interior point of x minus a. Right. Which shows that it's open.
So that what would that show?
The x minus a is open.
Ah,
Should say it's closed.
very good. So if we can prove this, then we've got that. This immediately implies then that A is closed, right? Okay. So this implies A closed, which is what we're after, right? Okay. So then the question, of course, is why? Why is that true? Okay. Here's the argument. He says the product, the singleton X, Cartesian product with A, does not intersect, excuse me, the diagonal you guys tell me why this is. It does not intersect the diagonal.
Because x is not an element of
Right. Since X is not an element of A, right? So the diagonal is points X comma X, right? So if X is not in here, you don't have the pair X comma X to find in the intersection, which is the only thing you could hope to find in that diagonal, right? Because the only pairs you have here are ones with the first component being X by construction. Right. And since X is Hausdorff, all right, he says that let's see if we can follow this. Since X is Hausdorff, the singleton X Cartesian product with A is contained within the open set. Aha! You see why this is open?
Because diagonal is gone.
Yeah. And remember, if we complement by a closed set, we get an open set. I mean, by definition. Is it? I mean, okay, so basically he says call this thing W, right? Is it clear to you guys that X Cartesian product with A isn't, I mean, it's clear this is an open set. Is it clear that X Cartesian product with A must be in here? Yeah, because X Cartesian product A is not in the diagonal, right? So it has to be wherever it's not. It has to be outside the diagonal. It is, right?
Triangle.
Okay. The outside triangle, yes.
Side
Now
matrix.
we use Wallace's theorem.
Exactly. Now we use Wallace's theorem. So, by Wallace theorem, we have U, V, well, let's see here, U open in what? U, V open in X, right? Oh, both, it's X and Y are equal in this context, right? But we're looking at the Cartesian product of X and X. But if U and V open in X with X Cartesian product with A subset of U cross V subset of W, right? In particular, we have what? We have X as an element of U, and U intersect A is empty, right? Right. Which is what we need to prove that it's closed. ¿Es bueno? All right, I'm going to move on to the next one here. Corollary 4.49. If we have X and Y topological spaces, all right, and one X compact, then the projection mapping from the Cartesian product X and Y to X to Y again. This is a closed map. And two, if X and Y are compact, then X cross Y compact. What's a closed map?
Maps closed sets to closed sets.
Maps closed sets to closed sets, right. Okay, so how we prove one? So we suppose X is compact, right? And then what? We let C, a subset of X cross Y, be closed, right? So what he says is if P of C is equal to Y, then we're done. Which makes sense, right? Because the Y is topological space, so it's closed, right? Otherwise, what? Let Y not be an element of P of C, right? But Y an element of Y, right? Then what? He's like, okay, so if you look at X cross the singleton Y, right? Then that's a subset of what? Let's see here, let's think about this. C is closed. So the Cartesian product of X and Y with this closed set removed is by definition an open set. This is the W in Wallace's theorem.
And X and singles and Y are both compact, so we can use Wallace.
Right, and yeah, exactly. The singleton is compact, and because it's finite, and so sorry, it makes me the proof that finite things are compact out makes me giggle because it's so stupidly simple. But yeah, X is given to be compact, and Y is finite. So yeah. And so yeah, we can apply Wallace's theorem. What does Wallace's theorem give us?
Two open sets.
So there exists what U, which contains X, right? And V, which contains Y, open, right? And what else we have? In particular, we have
V
X.
contains the singleton Y.
Oh yes, I'm sorry. That was supposed to be exactly. Thank you. So, putting this together, X Cartesian product. The oh, sorry, I jumped. I'm sorry. I was sort of. I'm copying a line from another proof. Idiot. This is fine. What does it mean though? It's just like X Cartesian product with V intersect C. I guess we probably need parentheses here like this, right? Otherwise it won't make sense. C is something in the Cartesian product, right? So I have to take intersection with similar objects of similar type. In particular, X cross V fits the bill. And this is what? Okay. So by Wallace's theorem, there's an open neighborhood V of Y such that the Cartesian product of X and V intersect the C here, closed set in the product is empty. And so that implies, what does that tell us? That tells us that V intersect with P of C is empty. Oh. Well, that's kind of disturbing. So the story is either P of C is the whole thing, or what?
Or it's
Close.
Or it's nothing. Or it's closed. Well, what I mean,
That tells us that V is in Y minus P of C. That means that Y minus P of C is open.
Oh, okay,
P of C
okay.
is closed.
I'm sorry. I was reading something that I was getting carried away here. Thank you. Bring me back down to earth here. So Y minus P of C is open.
Yeah.
All right. He says concerning 2, how do you get 2? Theorem 4.44, what we had. No, we didn't prove this one, but theorem 4.44, it said that if every fiber is compact for a closed map with a compact range, compact codomain if you like, then, I mean, theorem 4.4 we didn't prove, so I guess it's kind of inappropriate to prove this one too, but 2 is based on the thing I told you about last time, where we learned that if we have compact fibers for every point in the codomain, then you get compactness of the domain, given that you're working with a closed map. So if we have, let's see here. Right, so if so here, if you look at P inverse, of anything in Y, right? What's the inverse image of something in Y? Well, it's exactly X across the singleton Y. That's the fiber. These are the points which map to Y under the projection, and so the theorem 4.44 said if those are compact, that implies that the domain is compact, provided the mapping's closed. Well, we just proved P is closed up here. It's clear that the inverse image is compact if you're given that X is compact. consequently, by theorem 4.44, we get that the domain of the mapping, which, by the way, is this, x cross y is compact, and there you have it. The heavy lifting is back in theorem 4.44, which we have not proved. Okay, moving on, because there are actually really interesting things to get to today before we're done. Corollary 4.50 has the following. A subset of Rn is compact in Euclidean topology if and only if A is closed and bounded. That seems kind of important. Okay. I thought that the proof of this, which is given on page 78 of Minetti, it made me happy. Let's go over it together. It's very, very nice. And if it made me happy, that must mean that it's easy to understand, because I take joy when I can understand things in topology. Other people take joy in like Dedekind cuts, things that are technical and hard, and not so much me here.
Wait, what you said? Dedekind cuts?
Right, things like that.
What are those?
Way to construct real numbers
Oh,
using some sort of dividing process of intervals. I don't know exactly.
sorry.
That's actually no, it's fine. That's actually real analysis.
Yeah, I know
That's
real
worse. We'll talk about it.
Oh, yes.
You
Okay.
mentioned it in class.
Cool. Good. All right, here's the proof. So if A subset of Rn, right, is closed and bounded. What does bounded mean, by the way? It must be contained in
Some open ball.
right.
A finite radius.
But true, but more interestingly, I take your open ball and raise you an open cube, rather a closed cube, minus a to a, the n-fold Cartesian product of that, for some a greater than 0. You can easily see how to construct that from your open ball if you want, right? Now, for some a greater than 0, of course, right? But as we discussed previously, 0, 1, right, is homeomorphic to minus AA, right? And so
Minus A is compact. Minus A cross minus A is compact, and so on and so on.
yeah, so this is, compactness is a topological property, right? So if this is compact, that's compact by transference of compactness through homeomorphism. So then just what Daniel's saying. So what we then have is that right, through the inductive extension of what we proved over here. If you can do it for 2, you can do it for n. We have minus a to a compact, right?
So any subset of that is also going to be compact.
Right, so if you have a finite, for every open cover of this, you have a finite subcover, then you can use the same finite subcover to cover the thing this is inside it. I mean, finite subcovers descend to subsets, that's what I'm saying. So he says, so the Cartesian product, minus a to the nth fold power is compact, and so is any closed subspace in it, particular A. Conversely, if a subset of Rn is compact, then what? You can look at the map. What map are we going to look at? The map D sub 0, which is a mapping from A to the reals, defined by how? D0 of x is simply the length of x, right? In other words, the distance from the origin. That's certainly a continuous mapping. Right. So this is a continuous mapping. Agree? I mean, square root of the sums of squares is continuous. Differentiability has some trouble in certain places. But we're not talking about that. Continuous map. Oh, compact domain.
So D of A is also compact.
Right. So therefore, D0 of A is compact since it's the continuous image of a compact set into the reals. Oh, but what does that mean? That means that this is bounded actually, right? Because we're talking about a compact subset of real numbers. So D0 is the compact, hence bounded, right? So that means that you have, you have, how can I say this? 0 less than or equal to the absolute value, length of x, less than or equal to some constant m for all x in A, right? Which is to say it's bounded, right? But what else do I need? So we got bounded. Why is it closed? Rn is Hausdorff, right? You have a bounded, there it is, compact subspace of Hausdorff space is closed. So that implies closed. By corollary, 4.48. I love this marker. I wish I could get a whole pack of these things. It's really nice.
Where'd you get it from?
Christmas.
Oh.
It's one of those multi-packs. One of these. They're like, I don't know how much it is at Walmart. All right, so I just think that this argument is it's a nice argument. It's not terribly technical, and it really shows you why we've looked at everything we've looked at in the last hour and a half of lecture or so. It's all coming together. Like like Hannibal used to say, I love it when a plan comes together, you know.
With the theorem.
Yes, with the proper amount of cigar smoke. All right, and then corollary 4.0. Okay, so example, n spheres and closed balls are closed and bounded in Euclidean space, hence compact. So there we have it. That's pretty nice. Because if you think about what would be required to prove that they're compact directly, it would be less fun. Take any open cover of a sphere. I mean, I feel like I could do it, but it would be messy. Really messy. Just the possibilities of any open cover. Like, what does that entail? All right. Corollary 4.52. Let f be continuous from x to y, x compact, y Hausdorff. Then f is closed. Oh, okay. And if additionally f is bijective, it's a homeomorphism. Okay. It sounds like I was jumping statements, but it's kind of like a weirdly stated thing, so I mean. Do that here. deal f x to y. So here's the deal. F is continuous. And we're also assuming what? X compact, right? Y, what's the deal with Y? Hausdorff. What's the punchline? F closed. Right, and then if you add in addition, if F bijective, add that on, then you also get F homeomorphism.
Right, because we already saw the closed continuous bijection from homeomorphism.
Ah, very good. A closed, right. So really, so given that we already proved that a closed bijection is a continuous closed bijection is a homeomorphism, all we need to prove here is that that implies F is closed. So you take C as subset of X closed, right? Then you look at F of C. What do you got? I think I've erased the relevant theorem. Maybe I haven't. I don't know. What can we say? If it's closed in a compact set, it's what? What is in a compact space? What does closed imply? X is compact. Corollary 4.48, which what? Oh, it goes both ways.
Oh.
No, but that's not Hausdorff.
Oh.
What?
Why is Hausdorff? F of C
Did
is
I
going to be
do that
compact.
wrong? Any compact subspace of a Hausdorff space is closed. That's not the relevant one, I'm sorry. What do you say?
Okay, right. It's closed in a compact space, so it's compact. Right. F is continuous, so F of C is compact. Sorry.
Well, if I knew C was compact, then I understand it.
Isn't that the theorem you're talking about?
That was not, I said that, but that's not the case. I was thinking 4.48 was that, but 4.48 actually says any compact subspace in a Hausdorff space is closed. We don't know X is Hausdorff.
Right. But C is a closed subspace of a compact space,
Yeah.
so it's compact.
Why is that?
I think that's the theorem we looked at.
Okay, so that's what I'm forgetting. So the closed implies compact.
Right. That
Then
means
we
F
have-
of C is compact.
That implies that this is compact. Continuous image of compact is compact.
And Y is Hausdorff, so F of C is
Right.
closed.
Subset of Hausdorff, right? Then that implies closed, yeah. Which then says that the mapping is closed. So it's the stupid thing I just said a second ago. If you have a subset of a space which every open cover admits a finite subcover, it follows that a subset also admits
Yeah.
a finite subcover for every open cover it has.
That's 4.41.
Yeah, and we even proved that last time just by doing stupid intersection. It's just like intersection. It was not complicated, the proof of that at all. I'm an idiot. You guys have to be the memory that I don't have, if you don't mind. So, all right, so that brings us. That's it for that 4.5. So section 4.6 is on topological groups, and then section